Hello, everyone. So today we are going to talk about basic electronics and its role in intraoperative neurophysiological monitoring. The understanding of the different components of electronics is very, very important to perform intraoperative monitoring in the operating room. We are going to discuss different topics and stimulation and recording parameters, and I'm going to go and talk about different electrodes that are used for stimulation and recording. So let's go to the slide. So the review of basic electronics and the electrodes in intraoperative neuromonitoring. In order to understand the physiology of the neural signal generations and data acquisition, it's important to study their related electronics in detail. The signals are produced in the body, but how to record them and analyze them, the data, what is the best settings to record the neural signals of various frequencies, and how to interpret the data without any false positive and false negative during the surgeries. So the definitions of different topics start with the conductor. A conductor is a material that gives off electrons very easily. There is a free movement of electron in that material. Conduction is a process in which electrical current is easily passed through any conductor. The good conductors are silver, gold, copper, water, blood, etc. And the bad conductors are rubber, glass, wood, skin, etc. So any material that gives up the electrons very easily, which helps in uh, the free conduction of the current through that medium is known as conductor. Insulation or insulator. Insulator is a material that does not give up the electron easily. So insulation or insulator is opposite of a conductor. A material which is very easily gives up the electron is a conductor, and the material which does not give up the electron very easily is known as insulator. They have very high resistance to any current flow. Example again, rubber, glass, wood, plastic, etc. Resistance. So what is resistance? It is the measurement of opposition of flow to the direct current. So in a system, we have direct current and alternating current. The opposition to flow of direct current is known as resistance. Resistors are used to create resistance in the electric circuit. So when we want to induce a resistance in a circuit, we add different resistors, and the unit of the measuring resistance is in ohm. So you can have 1 ohm, 10 ohm, 100 ohm, mega ohms, 10 mega ohm, 20 mega ohm, very high resistors. So all the poor conductors, they have very high resistors, and all the good conductors, they have a low resistors. Impedance is a measurement of opposition to the current flow of the alternating current. So the opposition to the flow of a direct current is resistance, and the opposition to the flow of alternating current is referred as impedance. The impedance of electrodes is measured to confirm the quality of the contact with the skin. So if you have a lower impedance, that means the contact between the electrode and the skin is good. If the impedance is very high, that means the contact between the electrode and the skin is bad, and you need to have a better placement of the electrode. The unit of the impedance is also in ohms, and the desired electrode impedance to skin for best recording is between 250 ohms and 2500 ohms. So we don't want to have impedance lower than 250 ohms for a single electrode or higher than 2500 ohms. So why we don't want low very zero resistance or zero impedance? The reason is when we have zero or very close to zero, that means it's a short circuit. You cannot have a zero resistance um, if there's a contact between the electrode and the skin. So and a resistance or impedance very close to zero, means that the two electrodes, the active and the reference, they are touching each other. So there's something wrong. So that's why we want to have, and if the resistance impedance is very high, more than 2.5 kilo ohms or 22,500 ohms, that means that the contact is very, very poor, and we need to prep the skin or place the electrode in a different way. So next is capacitance, and on the left side we can see the picture which represents the capacitor. It is usually drawn as a cylindrical structure with the two poles coming out, and in the circuit it is two plates not touching to each other, uh, facing each other. The resistor is it continuous and the capacitor is not continuous. The two plates are not touching. So capacitance is the function of capacitor to store an electrical charge. A capacitor is an element that stores the charge, and the function of the capacitor which storing the charge is known as capacitance. A capacitor temporarily stores the energy in the form of electrical charge. So any capacitor, when it stores the energy, it will store in the form of electrical charge. So the time it takes a capacitor to charge 63% of capacity is known as time constant, and the symbol uses tau. So time constant, any capacitor, so you can have a smaller capacitor or a larger capacitor. But depending on the capacitor, the time it takes for that capacitor to charge 63% of its capacity is known as time constant. The unit of capacitance is farad or F, and the symbol is tau. So if you look at this image, so we're looking at this image, there are two plates. So when there is no current flow, there is zero current before the capacitor and zero after the capacitor. Same as resistor, when you have no current flow through the circuit, there is zero current before the resistor and zero after that. When you turn on the current flow of voltage, the current will flow through the circuit, and the current before the resistor will be higher than the current after the resistor, because the resistor is causing opposition of the flow. It decreases the current flow. On the other hand, when you turn on the voltage, the current will flow in the circuit, but will be high current, the maximum current on the first plate, and will be no current after the second plate. So once the first plate reaches 63% of capacity, the current will jump to the next plate and start flowing. So current will flow only after the first plate reaches the 63% capacity, and depend on how quickly it reaches to that, and that is known as time constant. So once we stop the voltage, turn off the current flow, in the resistor, there's zero current before and after. On the other side, in capacitor, there is zero current before on the first plate, before the first plate, but after the second plate, there will be still current flow. So the current charge on the first plate will be discharged to the second plate, and it's still flowing until it decreases and reach the 63% of its capacity. So it is very, very important to understand that the current and one of the reason it is advised that when you open any electronic TV, DVD player or stereo or computer, you should not touch the electronics bare hand. You must be grounded, because if you touch anything, you might touch the capacitor and discharge the stored current. So let's talk about current. So the movement of the charge or electron from a positive to a negative pole is called current flow. So the electrons flow from the positive pole to the negative pole, and that results in the current flow from negative to positive pole, and that is the uh, flow of the current. So the flow of the for if you're taking the exam or understanding for the IOM purpose, the movement of the electron is opposite to the movement of the current. So the movement of the electrons are from positive pole to the negative pole, and movement of the current is from the negative pole to the positive pole. The amount of charge flow per time in unit is known as current. So the amount of charge, the charge which is flowing to the circuit per unit time is called current. The unit of measuring current is I. So I is used as the symbol, and the unit is ampere, and you can use 1 ampere, and the subunit is milliampere. So 1 ampere will have 1000 milliampere. So how the electricity works? There are different. There are two types of electricity, as mentioned earlier: alternating current and direct current. The alternating current moves back and forward uh, with the changing magnetic field. This is a type of electricity from wall socket to your home. So the current we use in the wall socket for regular house and offices, the current coming is alternating current, and the reason it's known as alternating current because it keep moving, switching between the phase. So there's a phase shift, so it's a positive and negative continues um, uh, during the flow. On the other hand, the direct current, the current travels only in one direction, and this type of is usually is in the battery. So car battery or regular batteries, all the batteries have direct current, and the current moves only in one direction. So alternating current is kind of sinusoidal, but direct current is not sinusoidal. So if you're looking at the alternating current, so the blue line you can see is going up and down, up, down. It given on the other side, the direct current, the red one, it stays on the same voltage in the same direction during the um, flow period. So again, another example, alternating current versus direct current. On the right side, direct current flow only in one direction. So it's moving from negative to positive. And the alternating current, it moves in alternating fashion. So next one is voltage. Voltage is a force created by the difference in 2 points that would drive an electrical current between the 2 points. So voltage is nothing but a difference in charge between the 2 points. So the difference between if the difference between the charge is much higher, there will be high voltage. If the difference is low, there will be low voltage. So when you have a battery or the power outsource, so there are two poles, positive and negative, and the difference in charge between the two will result in a current flow. If there's no difference, there will be no current flow. The unit of measuring voltage is in volts, and the sub-units are millivolts and microvolt. So there are 1000 millivolts in 1 volt and 1000 microvolt in 1 millivolt. So there are 1 million, 1000 times 1000 is 1 millionth. So there are 1 million microvolt in 1 volt. So time constant, as mentioned for the capacitor, the time constant is the time it takes the capacitor to charge 63% of total capacity. Time constant is inversely proportional to the cutoff frequency. FC or cutoff frequency, if the cutoff frequency is higher, the time constant will be low. If the cutoff frequency is low, the time constant will be high. So the time constant is inversely proportional to the cutoff frequency of the filter and directly proportional to the RC circuit's resistance and capacitance. So the resistance, so the resistance is high, the time constant will be high, or capacitance is high, the time constant will be high, and vice versa. If the time constant, resistance and capacitance are low, the time constant will be low. But the cutoff frequency is low, the time constant will be higher, and the low time constant means high cutoff. Therefore, if time constant is short, cutoff frequency will be high and vice versa. It applies to both low frequency filter and high frequency filter. Longer time constant for low frequency filters and shorter time constant for high frequency. For the formula, time constant TC is equal to 1 over cutoff frequency or FC. So you should remember the formula. So there are few formulas which are used. So it's always good to make a note and keep on the one side, on one page, and all the formulas used during the monitoring. So time constant is equal to 1 over cutoff frequency, or cutoff frequency is 1 over time constant. The next is Ohm's law. So Ohm's law is based on three components: voltage, current, and resistance. Voltage is also mentioned as power or E. So V is voltage, I is current, and R is resistance as we, or impedance. Uh, and the same formula can be derived as E for voltage and I and R. So the Ohm's law states that voltage is always equal to current into resistance, or E power is equal to current into resistance. V is equal to IR. If if you are using a constant voltage stimulator, you want to keep the voltage constant. So the current will fluctuate depending on the resistance, because voltage is equal to current into resistance. If the resistance is low, the current will high, and if the resistance is high, the current will be low. If you are doing motor evoked potential, for example, or using constant voltage stimulator in any other case, and you see the current is very, very high, that means the resistance is very good. Your placement of the electrode is optimal. If you see low voltage current flow during your motor's voltage stimulation, that means your resistance is high. So you need to go and change the electrode, stimulation electrode, or recording electrode, or you can just uh, another area where there's less, better skin contact. If you're using a constant current stimulator, the current will stay constant and the voltage will change depending on the resistance. So for constant current stimulator, I is equal to voltage into resistance. I is equal to V over R. So if resistance is less, the voltage will decrease. If the resistance is high, the voltage will be high. If you want to find the resistance in the circuit and we have voltage on current, resistance is equal to voltage divided by the current. So we divide the voltage, amount of voltage, and the current by the amount of current flow, we will get the resistance of the circuit. What is differential amplifier? So differential amplifier has a very significant effect on your monitoring. A differential amplifier cancels the signals presented in common mode to the two input, which are positive and negative, and will amplify on the difference between the two inputs. So as the name says, differential amplifier, it is a component and usually presented as in the picture on the right lower corner, the triangular, two inputs and one output. It, it differentiates between the two input and amplifies the difference between the two input. So what is the difference? It only amplifies the difference, and anything which is in common to both of them, it will cancel out. That is known as common mode rejection. So a signal presented to the two inputs in a common mode will be rejected and the difference will be amplified. There are two inputs. The first input is known as active or negative input. The active negative input is also known as inverting input. And what is the significant? The main significant is any signal which enters to the active input of the differential amplifier, it will be inverted. If it is a negative input, it will become positive. If it is a positive input, it will become negative. A negative input means the signal is going down. A positive input, it means a signal is going up. So and that is how it is recorded in the system. It is not how it appears on the screen, because the appearance on the screen is depending on the input of the amplifier. So if you say N20 is a negative peak at 20 millisecond, that means before that signal is entering into differential amplifier as being recorded from the scalp, from the somatosensory cortex, it's a negative potential going down and it take 20 millisecond from the site of stimulation. Once it is plugged into differential amplifier, the negative becomes positive. So it displayed up as going upward peak on the screen. So the same signal, if we put the input into positive input, the second one, it will not invert and it will stay downward. So if your N20 is going down on the screen, that means it is entering or it is being recorded either from the precentral gyrus or the phase reversal, or you have plugged in into the positive input. So the second input, The reference input is known as positive or non-inverting input because it does not invert. The input impedance is an impedance of a resistor between the two inputs. So there's a very high resistor and there's supposed to be very high resistor between the two inputs, right between negative and positive. So the current doesn't come in, the signal doesn't come into negative and come out of the positive. So in order to push this more forward, a very high resistor is placed. So the signal does not cross that resistor. And that is known as input impedance. So input impedance is the impedance at the entry of differential amplifier. It is not the impedance of the electrode. The regular impedance, when we talk, we're talking about the impedance of the electrode at the in the recording side. But this is a different than that. Of So according to the guidelines, the minimum input impedance should be 10 mega ohm or higher. So it should not be 10 mega ohm. So the minimum input is 10 mega ohm or higher. So the property of the differential amplifier which cancel the signal in common mode is known as common mode rejection or CMR. The common mode rejection is a ratio of how many times the signal will be cancelled and how many it will pass. So when we apply the same signal again and again on the same input, 10,000 times and only one time it will pass after 10,000, that's an acceptable differential amplifier. If it is passed more than one, that means it's unacceptable, it's a bad differential amplifier, and we cannot use that. So if it's 20,000 to 1, that's much better. But if you apply the same signal on negative and same signal in positive, they will cancel each other out, and every time you apply. If only once in those 10,000 times it pass, that is okay. So that means that we have error rate of 0.00001. So it's almost impossible to make anything perfect. So there's always an acceptable range of the error. So the acceptable range is that less than 0.00001. If it is more than that, that means it is a bad differential amplifier. We cannot trust them. The reason the two will cancel out is because, as we talked, the first input is a negative input, the second is positive input. So the signal is not A minus B. Input A is A and input 2 is B. So the formula we use is minus A plus B. So it always addition of input 1 and 2. But before we add the two input, the input A becomes inverted. If it is negative, become positive. If positive, become negative. So if there's a signal minus 2 more microvolt coming into the active input, and the signal which is 2 microvolt coming into the positive input, so it will be minus 2 will becomes positive 2. So it'll be 2 plus 2 plus 2, it will be plus 4. So it will be a 4 microvolt signal going upward on the screen. If it is 2 microvolt signal coming into the active input and minus 2 microvolt coming into the reference input, the plus 2 and the active becomes minus 2. So minus 2 plus minus 2 will be minus 4 microvolt on the screen. So the signal will show on the screen as downward 4 microvolt. If the signal in input 1 is plus 2 microvolt and a signal in input 2 is plus 2 microvolt, the plus 2 in input 1 becomes negative 2. So negative 2 plus 2 will become 0. So the output will be 0 output. So that's the how formula work. And if you get any question in the exam or you're trying to solve what should be the size of the output signal and what should be direction of that signal, you always use that formula minus A plus B. Whatever is in A becomes inverted plus add to the input 2. So the amplification of the amplifier, how much its amplifier is known as gain. So that means how much we are gaining the signal. So gain of the amplifier, differential amplifier if we use the formula, use voltage out divided by input voltage. So if the output voltage is 10,000 and input voltage is 10, that means 10,000 divided by 10, 1,000. So the gain of the amplifier is 1,000. So if output is 1, input is output or input is 1, 1 over 1 is 1. So the gain of the amplifier is 1. That means there was no amplification in that signal. So that is another formula to remember. Gain of the differential amplifier is equal to, gain is equal to differential amplifier. Um, Gain is equal to voltage output divided by voltage input. So the polarity, we talk about the polarity. Polarity is the direction of the signal. So, and we need to understand the two polarities. The polarity is of the signal before entering the amplifier and after the signal. So if you say there's a negative signal, so you need to be precise. The signal is negative before it enters the amplifier, or negative after it's flipped or inverted. The sensitivity, we are going to talk about it again. Sensitivity is a zoom in, zoom out phenomena, how the signal appear in the screen. So this is the actual more precise picture of the differential amplifier. So see, we have inverting input, which is negative input, and we have non-inverting reference input plus, and there's a circuit. The resistor between the two is known as input impedance, and that has to be 10 mega ohm or higher. So the two output of the two inputs, they are combined, they are added, and voltage out. And this, the amount of output voltage depend on the gain of the amplifier. In the input was 1 and the gain is 10, the output will be 10 microvolt on the screen. So some examples of the differential amplifier from the book. So if the negative signal is going up and there's no signal in positive, the output will be downward signal. So negative upward, this positive signal become negative, and adding to 0 will be negative. If it is 0 signal in negative and plus 1 in positive, this will same 0 plus 1 will becomes plus 1 upward signal. If the negative signal in input 1 and 0 signal in input 2, the negative becomes positive, so the outcome will be going up, positive signal on the screen. If the negative signal in positive and 0 in negative, then the output will be negative, so there'll be non-inverted, it will stay the same. If there's a negative signal in input number 1 and positive signal in input number 2, the negative becomes positive, and if they are of the same latency, they will be like they will add the amplitude and will be positive on the screen. If the input number 1 is negative about 2 microvolt and input is positive 2 microvolt and input 2 is plus 1 microvolt, the plus 2 microvolt becomes minus 2 microvolt, and minus 2 plus 1 will becomes minus 1, 2 minus 1. So it'll be 1 microvolt downward. So what is gain? Gain is the property of differential that is exempted by the amplification factor. A differential amplifier amplified the input voltage by its number, by this number gain to have an output. Gain is always presented mathematically as gain is equal to voltage, output voltage, and input voltage. So that's the formula we should remember. What is frequency? So frequency, so any signal, the frequency is the number of cycles per second. So depending on a signal, a sinusoidal signal or any signals which is occurring, the number of time it's occurring in 1 second is known as frequency. If the signal is occurring twice per second, it's at 2 hertz, and the symbol is hertz and the unit is hertz. So if signal is occurring at the rate of 10 times per second, it will be 10 hertz. 100 times will be 100 hertz. Sampling rate is the number of samples per second. So the number of so once we have a signal and we have a frequency of specific signal, we can have a EG signal between 0 and 30 hertz. We can have SSB signal at a different frequency, EMG much faster frequency. So we have to sample that, and so it's a analog signal, and we have to convert it to a digital signal through the IM machine, and then digital signal is converted uh, it's a converted digital signal by using an analog to digital converter, uh, and that signal is analyzed digitally, and after that it is converted from digital to analog converter, and it displayed on the screen as a analog signal. So in order to make that signal as close to the real signal, you have to take the samples of that signal very, very fast. If the sampling is very, very slow, it will be a distorted signal. It will not look like the same. So sampling rate is number of samples per second to convert an analog signal to digital converter. Nyquist frequency is a sampling at least twice the maximum frequency in the signal. So Nyquist frequency is a minimum frequency rate, and we can do it higher than that. And that means that so you have multiple frequency in the signal when we are recording. So the sampling should be minimum the twice the highest frequency in the signal. If you're sampling below that, it will cause distortion of the signal, original signal, and is known as aliasing or aliasing. So if you look at the picture on the right side, we have number A. So it's like 3 hertz signal. And if you take, so if you 3 hertz signal and we take 3 hertz sampling, which is 3 samples per second, so those will be equally inverted and it will show on as a straight line on the screen, because when you join those 3 data points at the higher peaks will be straight line. If those 3 samples are at the bottom peaks, there will be straight line at the lower amplitude. If we sample at 6 hertz, which is the twice the highest frequency in the signal, is B. So the first one, A, is sampled as F, which is frequency. B is sampled as 2F, twice frequency. So you have 6 samples, and it will look like this zigzag signal. So this is not as good as the real signals. Our clear sinusoidal signal is more very sharp up and down peaks, but it is more close to that original signal than A. If we stimulate 4 times the frequency or 4F, we'll have, uh, we stimulate only 4 times instead of 3 hertz, we're stimulating at 4 hertz. That will create a distorted signal which look different. So we do, so we want to have like signal at least two frequency, 2F, or 4 or 5 or 6 or much higher than that. So higher frequency of sampling, much better sampling rate, and you can record at a multiple curves of the sample signal, and you have a much better presentation. So filters, any signals, once they are sampled, they go to filters, and filters allow us to get rid of the unwanted signal. So if you are recording as a sensory evoked potential, we don't want EEG or EMG signal. If you are recording EEG, we don't want SSP, EMG, and other signal in that data. So in or also noise, 60 hertz noise and other noise, EKG noise, artifact, and other signal. So in order to get rid of unwanted signal, the processing is known as filtering. There are multiple filters. The most common one are high pass, low pass filters. So high pass filter is this the first one, and pass filter is the first one. So any signal, it is also known as low cut filter. And why it's known as that? Because a high pass filter will allow all the signal to pass above that point. So it will be a lowest cut point. So it will be low cut filter and a high pass filter. So the low pass filter is also known as high cut filter because it will cut off everything higher than that point, and it will pass only lower than that. So low cut filters and high pass filter are same, and low pass and high cut filter are same. When we combine the two of them, we get a band pass filter. Band pass filter mean you are just letting a bandwidth of fixed between 2 points, 10 or 100, or 10 or 30, or 30 to 500. So you're picking a low cut point and high cut point and allowing the signal, only that signal to pass. So depending on the frequency we are monitoring, so we just set the filters, band pass filter for that setting, and we use that data. Another filter that can be used is a notch filter. Notch filter is used to get rid of 60 hertz noise. So if you are in the US and some other countries, there's a 60 hertz noise. All the electronic component are use 60 hertz noise. In Europe, Asia, and some countries, the the current is 220 volts, 50 hertz. In US, it is 110 volt with 60 hertz. So if the signal, the electric current is 50 hertz in the country, then we use 50 hertz notch filter. Another important part about these filters we have seen, they have a slope. So the signal is not, um, if you set up the cutoff frequency at this point, the signal does not cut off in 90-degree. It will start cutting off before and it will keep moving forward. And that is known as slope. So the signal, the maximum, if it is 30% drop, so the point at which the 30% drop, that will be known as -3 decibel. Um, no, -3 decibel cutoff frequency. So there's always a slope which involves signal more filtering above and below that point. Um, more filtering for the high cut filter, more filtering on the above, and low cut filter, more filtering on the lower than that, and some filtering on the other side. For the notch filters, there's also slope. So if you use a 60 hertz notch filter here, so the slope will start at about 47 hertz and it will stop at 73 hertz. So signal from 43 to 73 hertz, they are 47 to 73 hertz are affected. And if it is a sharp um, filter, then it will be about 57 to 65 hertz filtering. But it is not only 60 hertz filtering. So notch filter is used for for um, getting rid of 60 hertz noise in the signal. There are two factors which inhibits or prevent us for using notch filter in every single case. One is called phase shift, and the second is uh, ringing effect. The phase shift means the phase of the signal is delayed. So if you have a notch filter, if this is the signal and you turn on the notch filter, there might be a shift in the phase of that signal. So, and if that will look like a delay in the signal. So that's why one of the reasons you don't use 60 hertz notch filters or 50 hertz notch filter. The new filters, they are known as zero phase shift notch filter. So if you use zero phase shift notch filter, they will not cause any phase shift. The second phenomena is known as ringing effect. And the ringing effect is if you have a signal, any signal, there's always a stimulation artifact in the beginning, and then we have a response, evoked response. So um, if you use the notch filter, that stimulation artifact, so it's a ringing of the stimulation artifact. It is not the ringing of the signal. So that's a very important point to remember. It is the ringing of the stimulation artifact and not what is the ringing after. So this stimulation artifact, instead of stopping at zero, it will keep going on depending on. So it will superimpose the response depending on how late an early response is, and we will not be able to see the response. So this ringing will distort the signal and we will not be able to. So anytime we are using Evoked response, that means there's a stimulation. We don't use the notch filter in that case. So sensory evoke potential, motor evoke potential, auditory evoke potential, visual evoke potential, trigger EMG, these are all evoke potential, and they have a stimulation uh, artifact in the beginning. So notch filter should never be used in these EEG and spontaneous EMG are the only two. If you use a notch filter, then there is no stimulation artifact, so it will be okay, except for electrocardiography. So when we're doing electrocardiography or EEG direct from brain cortex, we don't use notch filter, and the reason is that the spikes or epileptic activity can occur at different frequency, and if using a notch filter in these surgeries, that may result in attenuation of the signal. So that roll off, so we were talking about the roll off. All filters are not perfect, and the set point for the cutoff frequency called the roll off slope defines the roll off frequency. The roll off characters are function of the time constant of the RC circuit, which is resistor and capacitor, used to perform the filtering. So we have low cut frequency filters and high cut frequency. So we have two frequency signal. The function of the lower frequency filter is to remove and attenuate signal below a set cutoff. For example, using 30 hertz or 10 hertz, the frequency above that cutoff will pass and the below will be rejected or attenuated. For example, at minus 3 decibel point, which is a point of the cutoff where the signals drop to 30% of its amplitude, the signal reduced by 3 decibel or 30%. The slope is usually given in decibel per octave. Octave is twofold, so that means 2, 4, 8, 16. So every decibel, there are two per. Uh, so slope is given in 2 decibel per octave. The high cut frequency is a function of high frequency filter to remove or attenuate the signal which are above the cutoff. For example, 500 hertz. So all the signals above 500 will not pass, and everything below 500 will pass. So high frequency cutoff filter is also known as low pass filter, and low frequency filter are known as high pass filter. So below that frequency, cutoff frequency for high cut, will pass and above will rejected or attenuated. For example, at minus 3 decibel, which is again 30% drop, the slope is usually given in decibel per octave. The roll-off slope is the frequency range from, so the roll-off, the slope, because the slope is going to start below that minus 3 decibel point. So minus 3 decibel, the signal is reduced at 30%, but it starts decreasing before that, as we saw in the previous picture. So roll-off slope is a frequency range over which the filter still passes signal around the set point. In contemporary machine, the roll-off frequencies are robust. In IUM, the minimum roll-off slope for low frequency filters is 12 decibel per octave, and for the high frequency is 24 decibels per octave. A filter with roll-off slope of minus 12 decibel per octave will have a sharper slope than minus 3 decibel per octave. So if the filter is decreasing the amplitude minus 12 decibel per octave, that will have a much sharper uh, cutoff as compared to minus 3 decibel. The frequencies are attenuated over a range around the cutoff frequency. So whatever the frequency we set up, high cut or low cut, the frequency above and that point, they are all affected. So if you're looking at the picture of this uh, slope, so we can see this orange high frequency filter. So I have high decibel, and as the frequency increases, the slope decreases. For low frequency filters, as the frequency increases, the decibel increases, the slope increases. So for any system, we need to have a good resolution, and there are two components of resolution of the screen or a resolution of the signal. We have a horizontal resolution and we have vertical resolution. So what depends on these resolution? The horizontal resolution They are vertical columns. If you look at the picture, the blue columns, they are vertical lines. They are they represent the horizontal. So those lines, they are not going up and down. So we are counting them going from left to right. So it depends on analysis time and the dwell time. So the horizontal resolution depend on the sweep, the time of recording or analysis time, or the time between the samples. So if you have less time, the resolution will be better. If the time between the two data points is higher, longer, then the resolution will be poor because the curve will not pick up the signal as clear. The vertical resolution, which is going up and down, red lines, they are depending on these red lines from going top to bottom. So the vertical resolution, they create the horizontal lines. The horizontal resolution create the vertical lines. So vertical resolution depend on size of the analog to digital converter or ADC. So what formula we can use for ADC conversion? The formula is 2 raised to power n, where n is the number of the bits. So if it is a 8-bit analog to digital converter, that means it's 2 to power 8. So it's 2 times 2 times 2 times 2 times 2 times 2 up to 8 times, which is 256.2 times 2 is 4, 4 times 2 is 8, 16, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and then we have 256 data points. The 10-bit has 2 raised to the power 10. It has 1024 data points from top to bottom, and 12-bit it has 4096 points going from up to the bottom of the screen. So uh, 8-bit analog to digital converter has 256 points, 10-bit has 1024 points, and 12-bit has 4096 points from top to bottom. So a 12-bit analog to digital converter have many 4096 points from top to bottom. So the screen resolution will be much better as compared to an 8-bit converter. So what is analysis time? Analysis time is the duration during which the data is collected after stimulation is triggered. So the total time which we need for recording the data is known as analysis time. The other terms which are used are analysis period, sweep time, time base, epoch, and epoch time. So all those points, so they're all different names, but it is analysis time. So the green, the whole time required to record is analysis time. The time between the two recorded sample is known as dwell time. So we are sampling around the screen. The computer is sampling across the signal, and the time between two samples is known as dwell time. The formula is another formula. Dwell time or dt is equal to 1 over sampling rate. And sampling rate can also be, if you have just a dwell time, you can also calculate the sampling rate, which is equal to, so sampling rate is equal to 1 over dwell time. They are inversely proportional to each other. Signal averaging is another term uh, for understanding how the signal is produced. So in order to reduce the background noise and record physiological signal, and averaging of a signal is required. So how we do that, and why we do that. So when we are recording the signal, so there's always a background noise in the signal, and we want to get that because the body signals are produced in a very small amplitude. The size of the signal is very, very small, and your noise is high. So, so in order to get rid of noise, when we average, so the S, if the signal every time we stimulate, the signal side will be the same. It will be produced at the same location every time with the same amplitude. So if you have some average of signal, it will still remain the same. It's not going to change the signal. So the amplitude will stay same. If you take once average, 100 average, 1 million average, the signal will not change. But the noise is random. So noise is positive, negative, or different amplitude. So when you average the noise, it decreases the noise. It cancels out. It never comes to zero, but it tends to zero. So when you increase the number of averages, the noise is reduced, but the signal comes out. So So the reason we do signal averaging is to get rid of the noise. So analog to digital conversion. So in order to change the signal from analog to digital, we need to do sampling. As we were talking earlier, the signal must be sampled at discrete time points to represent bioelectrics analog signal digitally. So the sampling and the sapling, it depend upon the frequency of the signal, and the minimum sampling need is Nyquist frequency. That's the minimum one. So we always sample much higher than this, the Nyquist frequency, but we cannot sample at or below Nyquist frequency. The time between sample is called binwidth sampling interval, which is 1 over sampling rate. The 1 second signal sample 100 times at equal interval would have a binwidth of 10 milliseconds. There are 1000 millisecond in 1 second. So 1000 divided by 100 is 10. So you sample 100 times in 1 second equal interval. That means each signal will be 10 millisecond apart. The bin width depends on the sampling rate, since a sample is taken with each new bin, and new sample cannot be taken before the end of preceding bin. So the sampling rate is again is inversely proportional to the bin width, and the reason is the new sample cannot be taken until the first sample is completed. So 1 over bin width is equal to sampling rate. The sampling rate R and bin width R is separable. An increase in bin width, so if there's an increase in bin width, it means that decrease in sampling rate. And if it is decrease in bin width, that means the sampling rate is increased. An example, sampling rate of 100 hertz, the sample is recorded at 100 times per second. The minimum sampling rate required for analog to digital conversion IM is 20 kilohertz. So 20 kilohertz or 20,000 times per second is the minimum sampling rate required for any IM machine. So again, for 100 hertz signal, bin width is equal to 1 over sampling rate, which is 1 over 100, which is equal to 0.01 second or 10 millisecond. So if you want to remember the formula. Fast Fourier transformation, or FFT, just want to touch quickly. The FFT is a mathematical technique that deconstructs a complex waveform into component sine wave. So we have a sinusoidal wave, and we take the samples at a different interval, and calculating that to um, um, a digital format is known as fast Fourier transformation, or FFT. So it's a mathematical presentation of the sinusoidal wave. It's presented with a segment of data that represent the amplitude versus time relationship of a complex waveform, and FFT will derive uh, two set of results: the amplitude spectrum, which is amplitude versus frequency, and the phase spectrum, which is phase versus frequency of the signal. So there are two spectrum which are derived during by using the FFT. This information is sufficient to describe the relationship of the sine wave, which makes up the waveform, and the further computation, the FFT result can be interpreted for several different types of display. Signal to noise ratio. So the reason we do, as mentioned earlier, for the to get rid of noise is averaging. So the averaging is the we do to get rid of noise. But what is the signal to noise ratio? So the formula is important. So signal to noise ratio is defined as the ratio of the amplitude of the signal to the amplitude of the unrelated noise. This ratio is improved with the number of average responses. Mathematically, by averaging the signal, the noise decreased by the square root of the number of average. So mathematically, when we are averaging, the noise is increased by the square root of the number of average. So it's not a linear correspondence. If we look at this picture, diagram, the amplitude is going on the left side and the number of averages at the bottom. The signal is uh, the signal the signal is right here, which does not change the amplitude, but the noise is the one which is changing. So it's coming to zero. Initially, the noise is maximum here, but with number of averages, the noise is very, very low. So the formula we use is signal to noise ratio. New signal to noise ratio is equal to old signal to noise ratio multiplied by number of trials under the square root. So if you use this formula, if signal to noise ratio is 1 by 4, so the signal is 1 and noise is 4 times the signal. So the noise is 4 microvolt and signal is 1 microvolt. And so it's very, very suppressed. So you cannot see that. You want the signal twice the noise. Uh, so that means if the noise is 4, it will stay 4. And you want the signal to be 8. So moving from 1 to 8, we use this a number of averages. So how many averages we need to make a signal which is 1 by 4 to make it 2 by 2 to 1. So 2 to 1 is equal to 1 over 4 number of multiplied by the number of average into under root, and we want to find out those numbers. So it'd be 8 uh, equal to number of average under square root, and we take square of those, take out the square root, so it'll be 64 averages to do that. So common mode rejection ratio, uh, if we are taking um, the number of for the averages for the differential amplifier, so we use the formula 20 log of voltage out or voltage in decibel. So if you have a 20 decibel, uh, its anti-log it will be 10, and if you have 80, the anti-log will be 10,000. If you 100, it will be 100,000, and 120 decibel will be 1 million. Display sensitivity. So the gain of the amplifier is something which is permanently changed in the signal. You cannot reverse that. It's a irreversible change. The display sensitivity is how the signal appears on the screen, and it is reversible. It is zoom in, zoom out function, and it does not create a permanent change. So it's a factor by which an image is magnified on the display screen. So you are zooming in or zooming out. Changing the screen display will increase or decrease the size of signal on the screen without making any permanent change in the real raw data. So if you have a signal which is 2 microvolt per division and want to change uh, the display to 10 microvolt per division, the signal smaller of the screen where is the changing, so the signal will become much smaller. And if you change the gain from 200 microvolt to 50 microvolt, the signal will become very big. So if you look at this one, the signal, if it is 4 microvolt, so if the signal is 2 microvolt in size and your display is 4 microvolt per division, that means that the amplitude, the whole division is 4 microvolt. So the signal take only half of that time place area, which is green. If you change the display to 2 microvolt per division, so signal will not change, but because this box or the division is now 2 microvolt in amplitude, so the 2 microvolt signal will take the whole box. So it will becomes bigger. So when you change the gain to a bigger number, the signal will become smaller, and which change to a smaller number, the signal will become bigger. So we want to, if you want to, if the signal is very, very small, you cannot see in the screen, you can make it uh, set it to a smaller number. So when you're increasing the sensitivity, you're decreasing the number. When you're decreasing the sensitivity, you're increasing the number. Artifact reject is a property that limits the signal size passing through the analog to digital converter. So when we have a lot of artifacts that surgeon is doing Bowie or bipolar using or some other random noise, and you don't want that to be part of your signal, we use an artifact reject, and that is a setting where any signal bigger than that will be eliminated. So this eliminate all the noise and high amplitude background uh, above that point. It can be set up to 95% of dynamic range of the analog to digital converter. So you can set to 10%, you can set 20%. Much lower number you set, the signal averaging will stop, and it will not start until the signal is smaller than that side. So if you turn it off, you will have all the noise will be part of signal and you cannot contaminate it. So you need to have artificial reject on all the time, but set to a lower number, about 25 to 50% or 70%, depending how much noise you have. If you have too much noise, you cannot set to lower number because the signal will be stop, averaging will stop every time. The only time you don't want the artifact detector on is motor evoked potential, because motor evoked potential, we don't know how much will be the stimulation artifact. So if the artifact detector is on in motor evoked potential, um, it will stop the signal averaging. So you will stimulate, but you will not see any data on the screen. So artifact reject should always be turned off or unchecked for motor evoked potential. So what is dynamic range? Dynamic range is also labeled as input gain. It is set in microvolt per division. There are 10 vertical and horizontal divisions. So any IM machine, most of the IM machine, it will have 10 divisions for horizontally and 10 vertically. So if it's set, and we set the dynamic range to in microvolt per division. So if you set the dynamic range of a 10 microvolt per division, it will set the maximum range of the signal to pass 100 microvolt. So we set to 10 microvolt per division, 10 times 10 is 100. So any signal below 100 will pass, and any signal above 100 will be passed, but it will change the signal permanently. How it will change the signal? Any signal larger than the dynamic range will pass, but will be clipped. Is cutting off from the top and bottom. So the signal will be um, chopped off, and it will look like a square wave above and below. So if I want to draw this signal, so if you have this signal and your dynamic range is smaller than that, if this is the dynamic range and the signal is bigger than that, the signal will pass, but it will not be the same signal. So it will look like this. So this is called clipping. So the part here will be clipped and the part will be chopped. So the part which is bigger and above and below that dynamic range will be cut off. So it is different than the artifact reject. The artifact reject will stop the averaging. It will not pass anything. Dynamic range is letting the signal to pass, but will be clipped. The two large so one can say that why we don't use too large dynamic range, because um, if you have too large one, you're not worried about. But if you have the dynamic range is very high, then the signal it is like SSCP signal 1 to 5 microvolt from scab. I set the dynamic range. The minimum you can set is 100 microvolt, so it's still 95 microvolt bigger than that. Set to 10 20 microvolt, which is 200 microvolt, you will have unwanted signal coming to that, and that will contaminate. So you don't want a much higher 200 or 100 microvolts dynamic range. So it's very important because most of the computers they're labeled as a gain. So this is not the gain. So it is the input gain. It should be said input gain or dynamic range, which is the which affect your clipping of the signal. So if you see a most time you see clipping will be on your motor evoked potential. You see a signal flat on the top or bottom or both. That means your dynamic range or input gain is smaller. So you can go back to setting and increase that number. You will also see that in train of 4. So we talk about this one, the resolution depend on two factors, analysis time and dwell time. And the vertical resolution depend on analog to digital converter size. So depending on how many bits you'll have data points on the top. What is ground? In order to reduce the stimulation artifact, a large surface ground electrode should be placed between the stimulation and recording electrode. So when we stimulate, uh, the current also spread, the DC current also spread over the skin, and that causes huge stimulation artifact depending on patient to patient and depending on the impedance and the placement of the electrode. So we want to take out that stray current on the skin, and that can be done by placing the ground electrode, which will remove that stray current spreading over the skin. So you want to have a bigger ground, not a very small ground. So big ground, so it can absorb that all the current, very good impedance. So you don't want to just go and put the ground on the skin. So you want to make sure the skin is prepped. It's use a for alcohol pad with some kind of abrasive ointment, and and clean the skin very well. Take out the oil, dandruff, or any other um, anything on the skin, and then put the ground electrode. So the ideally the ground should be placed between the stimulation and the first recording site. So if you're doing SSAP, the first recording site is poplite fossa, so you can put in the shin or on the leg. Ground in all current IO machines have no connection to earth ground and also act as reference point for all recording electrode. So an old machine placing two ground was riskier because when you place the two isolated ground, then you have two. There's a difference in potential between the two ground. Any ground will have a charge. There's a potential on that. So if you have two grounds, if the potential is different, it will cause um, activation of the current flow, and that is known as ground loop, and that can be very dangerous to the patient if the current is going passing to the heart or vital structure. So ground that's create the white ground loop. So you don't want to ground loop which is caused by the placement of two grounds on the two different machines. But all because all the current machine have no connection to the earth ground, so you can place multiple ground on each pod or each head box. It's not going to affect. So if you're using multiple ground, just make sure you check with the manufacturer because there might be some old machines or machine which you're not supposed to put the two grounds, but most of the machine available you can use multiple ground. So let's go to stimulation. Stimulation. So there are different type of stimulation. The first stimulators, the first one I'm going to just talk briefly is monopolar stimulator. Monopolar stimulation is a type of stimulation when both anode and cathode electrode are placed far from each other. So monopolar is the surgeon is holding one pole. It could be an active cathode or an anode. Depending on type of stimulation, you can do cathodal or anodal stimulation. Um, and the reference or the if you're stimulating the cathode, the anode is very far. They are not to each other. So you're stimulating with only one pole of the stimulation. When using monopolar stimulation, a cathode is used to stimulate a nerve or pedicle screw, and anode is placed opposite to the recording site to avoid any anode blocking, or actually place a distal site so it doesn't cause. So the sensitivity of a monopolar probe is higher, and the specificity is low. So um, as compared to bipolar and tripolar stimulator. So what does that mean? That means if you're stimulating monopolar, you will be spreading the current over a bigger area. So if you want to identify the nerve through the tumor or the structure or bone, you'll be able to activate that. As but you will not be able to know which nerve is that and which exactly because you cannot be very very specific. In order to be very very specific, you need to use a bipolar or tripolar stimulator. With a bipolar, you are very very specific, but if uh, the nerve is or a neural structure is not close, you are not going to activate, and so the sensitivity of a bipolar electrode will be low as compared to the monopolar. So we in trigger EMG and uh, SSP we use cathodal stimulation or direct nerve stimulation or cranial nerve stimulation. The only time we use a monopolar anodal stimulation is cortical mapping. So if you're using Taniguchi or high frequency motor mapping, um, for cortical gray area, we use monopolar anodal stimulation. For subcortical, we use monopolar cathodal stimulation. So it's opposite for the. The second one is the bipolar stimulation. So the bipolar stimulation, the both anode or cathode are next to each other. So either they are next to each other or like on the top left and the middle uh, scrolls. So top left is your bipolar electrode where the two probes are next to each other. It's a straight, and the middle one on the top, the bipolar is a hook bipolar. So you have to hook and lift up the nerves. On the top right is also bipolar, but the cathode is surrounded by the anode. So this is known as bipolar concentric. So either you can have bipolar side by side or bipolar concentric. So bipolar side by side can be very close to each other, touching very, very close or far apart from different. So bipolar stimulation is usually performed for focal and localized stimulation. A bipolar stimulation is more specific but less sensitive as compared to monopolar stimulation. A bipolar stimulation is used for cranial stimulation, tether cord stimulation, rhizotomy, dorsal root rhizotomy, Blexus surgery, etc., etc. So monopolar for nerves, cranial nerves especially, monopolar nerve stimulation is used for identification of the nerve. But when you want to track the nerve, then you can switch to the bipolar stimulation. The third one is a tripolar stimulation. The tripolar can be hooked tripolar or straight. It could be curve hooked or a 90-degree hook. So it also come in 90-degree and the curve one. So it is a type of stimulation where both there are two anodes on each side and the cathode is in the middle. So you have an anode blocking on each side. So it's very, very specific. It minimize the current spread across the tissue. It is used for high specificity and less sensitivity stimulation, and mostly recording compound nerve action potential or CNAP from peripheral nerve to localize the site of injury, nerve fever, or nerve trauma. So when we are doing peripheral nerve surgeries or nerve action potential, we use tripolar stimulation and we use bipolar recording. When a tripolar stimulation used in these type of surgeries for peripheral nerve, um, it reduces stimulation artifact and causes the anode blocking toward the unwanted signal. So we can minimize this one. So, so when tripolar stimulator is used, it reduces the stimulation artifact and causes the anode blocking. So for any case where we want to be very, very specific and identify a focal point, we use tripolar stimulation. So let's go to the recording. So recording and different type of recording electrode. So a pair of recording electrode is used for monitoring, and that pair is known as montage. So montage is a pair of recording between the two electrodes. So a pair of electrode, so we cannot record from a single electrode. So we always need a reference as two different points where the signal and compare the size of the signal between the 2 points, and that is entered into differential amplifier, and we use that information. So a pair of recording electrode or a montage is required to record a response. There are two types of recording electrode, which are known as active electrode and reference electrode. So there's an active input and reference input of differential amplifier, which is different than the active input and which is active electrode and the reference electrode. So active electrode is different than the active input of the differential amplifier. What is an active electrode? A recording electrode placed close to the generator of evoked response is known as an active electrode. So any electrode which is placed close to a evoked response or a spontaneous response, it is known as active electrode. Typically, the active electrode is always plugged into the active or negative or inverting input of differential amplifier. This result in the flip signal or inverted response on the display screen. So the active electrode can be plugged into the active input of the differential amplifier. It can be plugged into the referential input. So the active electrode can go into active input, or active can go into the reference input. We usually put the active electrode into the active input of the differential amplifier, which inverts the signal. If it is positive, becomes negative on the screen. If negative, becomes positive on the screen. So so it's very, very crucial to make sure you don't confuse the active electrode with the active input of the differential amplifier. So any active electrode means that it is close to the signal which produced in the body. The reference electrode is opposite, is electrode which is placed far from the recording site, from the signal. So if it's an evoked response or spontaneous response, so this electrode which is far from the generation is known as reference. And typically, a reference electrode is plugged into the reference input of the amplifier, but the reference can be plugged into active input. So, but it doesn't mean you have to plug it. But if the signals are reversed, we can go and check that what's the problem. So there are different type of recordings. So again, we have two active electrode and the reference electrode, and then we have a bipolar and referential recording. A bipolar recording pair refers to a pair where both active and reference electrodes are placed close to each other. So the active electrode and reference electrode we talk about, if they are placed very close to each other, that will make it a bipolar montage or a bipolar recording. This result in common mode rejection. So we have a common mode rejection because both electrode are very close to the signal, and the signal far from that area will be in common mode. The signal which is very, very close will not be in common mode, but the signal which is far will have the same distance to the both electrode. So that signal will be cancelled out, and only the difference between two will be amplified. If a bipolar pair is used on the scap, it will cancel out all the subcortical signal which are at the equal distance from the recording electrode. A bipolar pair, when used in EMG recording for peripheral or cranial nerve EMGs, will more specific than so it will be more specific recording. So you can precisely identify because your both electrode are in the same muscle, or because oculi or mentalis, masseter, any muscle mentalis. So depending whichever muscle you are using, if you're using a bipolar pair, you will be more specific and precise and less, but will be less sensitive. So if the signal is a little bit far, you will not be able to do that. On the other hand, the referential pair is, is a pair where the active and the reference electrode are placed far from each other. So the active electrode is placed on the generator and the reference far from the them. So it will amplify this signal in the close up proximity of the active electrode. And so the active pair will be more sensitive but less specific because it will pick up the responses around that area, and so you will not be very, very precise. So a reference monitor can be used for SSAP, EMG, or EEG monitoring. So the last topic we are going to cover is the type of electrode, just giving you some examples. The different type of electrode we can use, and most of them can be used in clinical setting. But so number one is the surface electrode. So surface electrode are adhesive, sticky electrode. They come so they are so you can peel off the cover and just put on the exposed area. So when you're placing the surface adhesive electrode or sticky electrode, it's always recommended to place on clean and dry area. It should not be placed on a wet area. It should not be placed on a hairy area. There should not be any dandruff. There should not be any um, wax or any other material that will cause increase impedance of the electrode. So the electrode, so if they're like those two electrodes, they are used for those electrodes are used for stimulation. And if the electrodes are too far from each other, you are activating bigger area and you may be activating more than one nerve. So the signal will be huge and much good looking, but at the same time, it will be you will have a huge stimulation artifact. So if you have a huge stimulation artifact on your screen, so that means the distance between your electrode is too far from each other. So if you want to reduce the stimulation artifact, you can decrease the distance between the anode and cathode. So the term we always use for stimulation is anode and cathode. We don't say active reference. The active reference is always the term which is used for the recording. So the both cathode and anode, you can move them closer, so that will reduce the stimulation artifact, but on the same side, um, it will decrease the amplitude of the signal. So you have to play about from one patient to another patient, and depending on the condition, where you want to put the electrode. The other point is the cathode should always be proximal. The anode should be always distal to the recording site. So if you're doing sensory evoked potential and you're stimulating the peripheral nerve, you want to put the cathode more proximal, close to the spinal cord, because the current will, like median nerve, tibial nerve, peroneal ulnar, they are all mixed nerve. So the both sensory and motor units are activated and the signal is going in both direction. So if you, for example, if you stimulate the median nerve, the orthodromic sensory, which is a normal direction sensory, is going to the spinal cord. The antidromic sensory, which is the opposite, going to the hand area, hand or skin. Um, you're also activating the motor fibers. So orthodromic motor is going to the hand, which calls twitching, or trainer 4. You can do trainer 4 by that, or antidromic motor is going to the spinal cord. So if you're recording a signal in brachial plexus, that will be a mixed signal. Or recording with cubital fossa, it will be a mixed signal. It will have orthodromic sensory and antidromic motor signal. But when the signal reaches dorsal root entry zone, so the motor and sensory fiber, they split. So you have a ventral root and dorsal root. The dorsal root have no synapses until nucleus cuneatus and for lower nucleus gracilis. So the sensory is a normal route. The signal will pass and it go to the sensory cortex, thalamus, and somatosensory cortex. So it go to the nucleus, thalamus, and the somatosensory cortex. On the other hand, the motor fibers, when it enters the ventral root, it it reaches the synapse and anterior horn cell between the upper motor neuron and the lower motor neuron. That synapse is one directional, so signal will not pass that. It will stop at that area. So it will stop at that area. That means when you record anything above that area, nucleus cuneatus, cervical or thoracic, cervical, thalamic or cortex, it will be pure sensory response, will be no motor. Anything until dorsal root entry zone will be combination of motor and sensory. Same for lower SSB. Popliteal fossa is a mixed response. Lumbar potential, when it is in small cord, then it have pure sensory, and subcortical and cortical, they are all sensory and no motor component in that. So, uh, so the cathode should be proximal, and cathode causes the normal resting membrane potential is um, I just want to so so if this is the nerve, the normal resting membrane is minus 70 millivolt, about minus 70 millivolt, 65 to 70 millivolt, and you have negative ions around inside, and you have positive outside. So when we stimulate, this is a normal resting membrane potential. So when you stimulate, um, so this is resting membrane potential. So the signal waveform increase on threshold, and then this is known as depolarization wave, that becoming positivity. So this is minus 70, somewhere about plus 35, or so, and then coming down is repolarization. So you have depolarization going up and the repolarization coming down, and but doesn't stop at the resting potential. It will sometime it hypershoot and cause hyperpolarization, and then it becomes resting. So this is really hyperpolarization. So you have depolarization, repolarization, and hyperpolarization. So that can occur during the regular evoke potential. So um, so when we stimulate, the cathode is negative, so it create a negativity outside the membrane and positivity inside. So sodium potassium pump, when it moves, so it moves positive ion inside, so called depolarization wave inside, it will make it positive, and inside, so that will be depolarization, and it will move in both direction. So that will be under negative. So under positive, it will cause it more positive outside and cause more negative inside, which is hyperpolarization, so which will block this transmission of the electrode. So this hyperpolarization under the anode is known as anodal blocking. Anodal block. So anodal blocking is caused by hyperpolarization under the anode. So that's so it minimizes or inhibits the transmission of signal, can disappear or can be smaller in amplitude depending on the hyperpolarization level. So that reason we should never put the anode between the stimulation and between the cathode or anode. So the other electrode, for recording electrode on stimulation, we can use gold cup electrode. So gold cup electrode, they are gold plated electrode in the cup shape, and there's small hole in the middle where we can put paste, and so if you put on the skin, they are not going to have a very high impedance. So you need to have a good conductive paste, and that will place that and secure on a one place. So these can be used for EEG, typically used for EEG. They are reusable electrode, and they're clean and then used again and again. Um, so that can be used for recording for SSP or EMG, and can be used for stimulation for SSP stimulation, or it can be used for MEP stimulation, depending on that. So they can be used for recording and both for stimulation. Another electrode we use is corkscrew. So if you look at the if this uh, the picture, so it's look like a screw. It's screwed. So this is screwed uh, on the scap, and this is used normally, it is used for motor evoked potential because it has a bigger surface area. So when the current is moving, uh, it is have less resistance as compared to needle electrode. Needle has the highest impedance opposition because the current is all the current is moving from one tip as compared to surface electrode, adhesive electrode we saw first, and these corkscrew because the bigger area. So if they are placed correctly, they have much lower impedance and less chance of burns during the surgical procedure. So these can also be used for recording SSAP or EEG in the craniotomy cases. So you can use for recording and stimulation. Subdermal needle electrode are used for stimulation and recording, both of them. Typically SCAP, SSEP, or EMG, and also for some people use for motor evoked potential. They are not. I don't like to use personally use for motor evoked potential. I prefer to use corkscrew electrode or gold cup electrode, but some um, depending on one place to another place, these can be used for any. So these are subdermal needle electrode, and they come in different sizes. So this is a typical 13 millimeter. They come in smaller sizes, pediatric 7 millimeter, and they come in longer. We'll see in the next picture. The ground electrode is a big electrode, so there are two different type of one small ground pad and bigger one. So the bigger one have a bigger area, so it has much lower impedance, and sometimes people will say, okay, this I use this, but the impedance was much higher than the needle, so I like to do. But needle is used very quick, and you just place it. But needle has much higher impedance, and you have more risk of noise as compared to the ground pad, because if you have a higher impedance in the ground pad, that means that the skin was not prepped and you placed it on the wrong place or without prepping the skin. So the skin is prepared well, and then it's placed, you'll have much lower impedance on the ground pad, and you'll have less noise. Hook wire electrode, so they are very thin electrode, usually used for cranial nerve monitoring. So there's a very thin wire which is um, pass through the needle, and it has a about 45-degree curve hook at the end. So when you insert into the muscle and take the needle out, it stays there. So this is for very precise, very specific recording. So it's used, very recommended, highly recommended for using for cranial nerve recording, for vocal cord recording, from soft palate, from tongue, facial nerve. So hook wire is the first option for using cranial nerve recording, because you can put two hook wire and you can have very low uh, impedance, and you will have very high specificity for this nerve. Um, the common mode rejection uh, is also better on this one. With the needle, some of the papers they say if you're comparing the two needles, subdermal needles, to two hook wire electrode, even the nerve is damaged, you may pick up a response in needle which is false negative, uh, which is uh, which is false negative, because uh, you don't see the change, but the patient woke up with deficit. And the reason is the needle pick up the cranial nerve or muscle nearby, but hook wire are less prone to pick up those responses. Epidural electrodes, they come in multiple contacts. This one is two contact, and so you can have two contact, three contact, four contact, so one, two, or three contacts. So one, two, or three contacts. Three contacts is the best one. So this one has one contact and one contact here, and you can see at the tip one contact here and one contact here. It's zero point 0.7 centimeter in diameter, and you have two DINs. So active and reference. So this is placed on epidural space. If the if the laminectomy is done, you can ask the surgeon to place the electrode, and we usually use one above and one below the surgical site, and for recording D waves and I waves from the spinal cord. So this is placed, if you're using three contacts, it has much better um, signal, because the distance between one contact and contact three is bigger, and they're both on the same. So if you have one contact, you can reference to a needle in the paraspinal muscle or skin, but that will have a high noise and less predictability. So two contacts is minimum, and you can use by three contact. So it is placed above and below the surgical site, and and always used for intramedullary, intradural, intramedullary tumor because they are at higher risk of post-operative deficit. So when you do motor evoked potential, patient jumps a lot. When you do D wave, it doesn't jump. So you do continuous D wave and in addition to MEP for a better post-operative outcome. The D wave latency, the tip is always number one, and then the second was two, and then three. So when we're putting the one, the op, so the active one is always active, and two or three is the reference. That the piezoelectrode at a lower level, the tip is so that the tip is reference, and the one three is active because when the current is coming from top, the three is the first and one is later, or two is first and one. When you're recording stimulating from up, the one is up and two down. So the surgery is here. It will be 1 to 3 or 1 to 2, or and the below will be 3 to 1. Cotton wick electrode is another electrode we use. So it's a very thin wire embedded in cotton at the tip and insulated uh, except for the tip. So this is dry, is because of the cotton. So you have to use a saline. You can ask anesthesia to give you like 5 cc of saline, and you can dip that and you can place. So this can be placed in against the tympanic membrane for recording electrococcygram. And this can be placed on the auditory nerve to record the data directly from the auditory nerve. So this can be placed on the nerve or can be placed on the tympanic membrane for recording. Bar electrode is used in the clinical setting, but you can use in the OR because they are reusable electrode. The other one are all disposable electrode. So there are two contact metal contacts. The distal one is cathode, and one of them at cathode and anode. It has is color coded on the other side, red and black. So the red is anode, and cathode red black is used as cathode. So you can put a gel and put on the skin on the surface, and you can stimulate median nerve, tibial nerve, any nerve, and it's a distance. So if you're doing clinical evoke potential, so you can use them in the pre-operative area, or you can use in intraoperative. You can just place and put a tape or tegaderm on top of them. Cortical grids are used for recording direct from the somatosensory cortex. The cortical grids come in different sizes, different shapes. Um, the smallest one is 1 by 4. 1 by 4 means that it has only 4 contacts, and um, so this is 1 by 4 electrode. So the 2 by 4 uh, will have this one, two, this is 2 by 6. So I have two electrode. This 8 by 8 has 64 contacts, so 8 rows and 8 columns. So 8 times 64. So and then you have 20 contacts with 4 by 5. So they come in different sizes, and then you have 1 by 8. So eight um, electrode. So we can place on the cortex. We can do intraoperative. We can also place and close the mm, the skin and place a patient in the epilepsy monitoring unit for long-term epilepsy, for long-term electrocardiography. So these are cortical grids. And we can use them for stimulation also. If you're doing motor evoked potential, you can pick up the grid which has a phase reversal on a premotor gyrus and use plug into the stimulation, and can use continuous MEP during the surgical procedure. So this is just this is same 1 by 8 grid. So the surgeon is placing the grid on the brain. So you have to make sure the exposed. So these contacts, they are they are embedded in silicon, and one side is exposed and one side is um, covered. So the export part should always be touching the cortex. If you on the other side, the export part is facing to the surgeon, then it will be all noise and you will not see that. Most of depending on the manufacturer, you can have a number 1, 2, 3, 4, and sometimes you don't have the number. The tip is always 1, and the most proximal is the last number. Ogen cortical stimulator is a stimulator which comes with the Ogeman stimulator, which is hard to find in the market because but it's a bipolar stimulator, and that and any other this can be used for bipolar stimulation, or any other stimulator can be used instead of this one. So direct nerve stimulation, again, direct cortical stimulation or direct nerve stimulation, there are different electrode. So you can have a ball tip electrode, which is a big bulbs. It's not sharp. and used for either pedicle screw stimulation for screws. You need a bigger, or cortical or subcortical stimulation for anode or cathode stimulation. The sharp tip, fine tip is used for direct nerve stimulation, facial nerve or peripheral nerve stimulation. Bipolar uh, side by side is used for nerve stimulation or cortical stimulation. This is the node stimulator, which is either have a fine tip or blunt tip. So fine tip and blunt tip is used for peripheral nerve or cranial nerve stimulation. The ball tip is a monopolar, so this is used as cathode, and the anode is used for a subdermal needle can be used as anode in the middle or nearby area or the contralateral side, depending on type of surgery for for a full. So this will be higher sensitive, less specific. The fine tip and blunt is not used for cortical stimulation or subcortical because it has very low surface area and then can go through the brain area. So ball tip is used for brainstem stimulation. So again, pedicle screw stimulator with a monopolar ball tip electrode used for pedicle screw stimulation, and they come in different sizes. So we have monopolar electrodes, fine tip, sharp tip, blunt tip. We have bipolar electrode. We have side by side bi tip or uh, so the distance between the ball tips can be very close by. So this is very close. This is a little bit further apart. There are again side by side. They are hook bipolar, and the last one is a tripolar electrode. So tripolar hook stimulator again, they come in different sizes. So you can have full hook and like a semi hook. They can also have a 90-degree hook. Small cord stimulators, those are the electrodes. They come in different size, uh, 8 contact, 4 contact, 16 contacts, 15 contacts, depending on manufacturer, and they are placed on the spinal cord for pain relief. It typically is done. Another story. Uh, it is done for pain relief for patient with failed back surgery syndrome. When they're going for multiple surgeries and the pain is not relieved, you can identify the area of the pain, left side, right side, leg, foot, by mapping of the spinal cord, and then place them, and the bed is placed on the abdomen, and this is continuous paresthesia. It blocks the pain fibers and help the patient. Hook electrodes, these are the longer hook electrodes. So we have two papers published um, on this one. So we can use for motor evoked potential and sensory evoked potential. They come in 60-degree and 30-degree and 90-degree curve, or they can split or hubbed. The hubbed are they're fixed, so the distance is fixed, and the split one is you can change the distance between the two electrode. The patient has a higher BMI, so you can use a longer electrode because if especially for quadriceps, the paper published was the quadriceps. So if you're recording a quadricep muscle in high BMI patient, you might not get any signal from a regular 13 millimeter. But if you record 25 millimeter or 37 or the 50, the longest one, 50 millimeter, so we have a success rate of 100% in 37 and 50 millimeter, but only 13% success rate comparing the same patient on 13 millimeter regular subdermal needle. So those are very helpful for patient with high BMI or the muscle which are deep muscle. The new one, bladder electrodes. So these are the two references I have for you for recording motor evoked potential and trigger EMG, two paper recording from patient. Uh, so these bladder electrodes, they are thin film which is stamped on Foley catheter next to the bulb, and it's a it's a bipolar electrode. It come in different sizes, Frank 8, 16, 18, 10, 14, and I think the only one of size 6, which is a periodic size for 8 months and less kids, size 6, which is monopolar, and you need to use a reference. The other one all bipolar. So we had a good success rate with recording trigger EMG and MEP from urinary bladder. Auditory evoked potential, there are multiple electrodes for stimulation and recording. So we have this um, receivers or transducers. So the term receiver is originated from the old telephones where we had the microphone and the receiver for sound generation. So they create sound, and one is red and one is blue. Red is for right side stimulation, left blue is left side stimulation, and they come with you can connect them directly to the tip, or you have an extension tube which is connected to the ear insert, which are foam ear insert. They come in three sizes, two colors. The beige one are for pediatric patient, and the yellow one are for adults. But adults, they are small and bigger depending on the ear canal, and the plastic, which is for the infants, newborn. Uh, on the right side, we have gold cup electrode. So the gold cup, gold foil, so same ear insert wrapped in the gold foil. So gold foil electrode has a connector which is used, can be used. The connector is usable, but these are disposable. So when you place them in the ear, so you can stimulate with the auditory sound, but you can use this gold foil as a recording electrode. So the gold foil is attached to, is connect touching the tympanic membrane, and the connector you can use as a recording for electrocochleography. Goggles. So goggles we use for visual evoked potential. So they're LED lights, red lights, and the flash. So on the left and right side, multiple VEDs. So you can use for uh, stimulating visual evoked potential. ERG electrodes. So for visual evoked potential, we have electroretinogram. So if you want to do visual evoked potential, we do record peripheral recording, which is recording from retina, or ERG electroretinogram. And these are the contact electrode. So you can place on the retina. So you have to be very, very skilled technologist and experienced with that. Have to be very careful with that because you don't. It has a metal ring which used as a recording from directly from the cornea. So you want to make sure that you don't cause any abrasions or ulceration on the cornea. So you have to put a transparent gel on top of that, uh, uh, and it has to be eye ointment, any antibiotic which is for use for eyes, not for surface or oral use. So use that, and it has to be transparent, not the opaque, and you can place on the cornea so it doesn't cause any abrasion. Deep brain stimulation electrodes. So those are another type of electrode which are used for deep brain stimulation. They come in different sizes, different contacts, full rotation, and can be used for various movement disorders. Parkinson disease. We have recording electrode and stimulation electrode. The recording electrodes are known as MER, micro electrode recording. So you go through micrometer by micrometer and identify of the target, which is depending if it's Parkinson patient, you go to subthalamic nucleus. If it is a essential tremor or dystonia, you go to VIM or some other nucleus, depending on disease. So these are FDA approved for most for Parkinson, essential tremor, dystonia, obesity, Tourette syndrome. So these can be used for, and then when the recording is done, you take out and then put the stimulation, which has multiple contacts, and you can pick up from contact one, two, three, four, or stimulate in one direction or the other direction. So, so that was a little bit summary about the monitoring for the basic electronics, which is used for intraoperative monitoring. Um, so the key terms, and it's very, very important to get familiarized by those one. So they will repeat again and again with all the evoked potential. So it's always good to have a good understanding of them. Thank you, and